going to talk a little bit more about determining stability of a system from its transfer function. We last time discussed how we can learn a little bit about stability without solving for the closed loop poles of the system. Recall that if you know what the closed loop poles are, you know about stability, right? But if you have a large polynomial in the denominator that's not easily factored, especially if there is some variable in the coefficients, so you can't do it numerically, then there can be an issue that arises, and you'd have to determine what the variable is before you find out about stability. So you have to sort of guess and check about stability, which is just not an ideal way to go about doing design, although we end up doing that often. What we did last time was determine that we could tell if a system was unstable based on just the coefficients. If they were all positive and there weren't any that were missing, then we would have potential stability, right? But if one of them was negative or one of them was zero, we would have the case where it was not stable. We would know that from just the form of the denominator. Now we're going to get a little bit more detailed in our analysis. We can find out even more about it without solving for the poles. And that's where this Routh-Hurwitz criterion comes in. So there's no practical way to find the roots of a polynomial greater than degree 4. If you want to look into the details of that, go to the reference there. An implication of this is that we cannot practically solve analytically for the poles of a closed loop transfer function with degree greater than 4. Fortunately, numerical root finders can handle these higher order systems with ease. Okay, it's not an issue. You can do it in MATLAB quite easily. However, there is a drawback to using numerical root finders to determine stability. Design parameters, which show up in the coefficients of the denominator polynomial of a transfer function, must be assigned a specific value. We don't want to do that when we're doing design. We want to be able to hold those parameters around and then tweak them at the end and see how it affects performance. So a couple of mathematicians in the late 19th century came up with a clever test called the Routh-Hurwitz stability criterion for learning much about the stability of a system without computing its poles. They weren't thinking about poles and transfer functions. Those hadn't been invented yet. They were thinking about solving for the roots of a polynomial. That's what they were thinking about. Moreover, the test yields an analytically tractable way to determine ranges over which design parameters yield stable closed loop systems, which is useful to know. You might have a system that you're designing and you have a parameter that you can adjust, but you don't know over what range of that parameter the system is going to be stable. So you go ahead and use this criterion, and it'll give you an ability to determine that. An algorithm for applying the Routh-Hurwitz criterion is the next subsection. We consider an algorithm for this test. First, we address the basic algorithm and refer the reader to the Nice textbook for the two exceptions that arise when column 1, or we're going to find out what that means, column 1 means, or an entire row of this table that we're going to build is 0. These do arise. They are dealt with in the homework, and in the Nice textbook it talks about how to deal with these exceptions, but I'm going to go over the basic one in class. I don't think that you guys will have any trouble with the extension. It's just like you have to modify the algorithm just like slightly, and then you can go off on your merry way, and it's almost exactly the same. You can teach this algorithm, including the exceptions, to a computer, as some have. So this is a MATLAB script that's pretty nice. It's up on the web that allows you to do this. MATLAB doesn't have a built-in, even in the control systems toolbox, to my knowledge, there's no way to find this, to do this test. So there is somebody out there who built one that's pretty nice. It's up on the web. But it is easy enough by hand for many systems. So that's why we're going to learn how to do this by hand. I would say this is, how I like to keep reiterating the fact that we shouldn't become experts at stuff computers can do, because we're not going to have any value as engineers if all we can do is execute an algorithm, right? That does not make us useful anymore. It used to be. I mean, it used to be an engineer, if you could compute an algorithm, if you could go through that and calculate things, that was like a useful task. Nowadays, we could have a computer do that, so why would we hire somebody at a nice salary to do that? Which happening less and less. They just will make a computer program instead. This is right on the border of still useful to be able to compute by hand, but I think it is still worth going through algorithms and understanding how they work, because it helps you get a feel for how to build your own algorithm and how to instantiate an algorithm. So it's good practice, although I will caution you not to get too caught up in learning how to do the algorithm and memorizing the algorithm. That's not useful, really. I mean, it is for the scope of this class probably, but it's not generally that useful. Understanding what it means and the use of it is much more important. So let the denominator of a closed loop transfer function with real coefficients ai be this. So a0, s to the n, plus a1, s to the n minus 1, etc. To an, where n is a finite integer greater than or equal to the order of the numerator polynomial, and this first coefficient here is greater than 0. And if it's not, in your closed loop transfer function, make it 0 by multiplying everything by minus 1 on the denominator and the numerator, and that will make it positive. So perform the following two steps. There's really only two steps to this. The two steps, well, the first of the two steps is a little bit involved. That's the construction of the Routh table. Okay. The procedure is to fill in the general form of the Routh table shown in table 2.1. So here is table 2.1, general form of the Routh table. If I left the cells empty, then they are 0. So these are columns. I labeled them 1, 2, 3, 4, the columns. And then the rows are labeled with powers of s, from s to the n down to s to the 0. This is actually a pretty complicated mathematical object that, if you want to understand why this works, there's like a lot of math behind this. Suffice it to say that it does work, and to execute the algorithm isn't difficult. Understanding how to use it is what our main goal is. And constructing it is also something we need to learn how to do. So let's learn how to construct it. So the first, so what you can always do when you start your Routh table is to fill in this label column of the rows, so s to the n down to s to the 0. So if your highest order is 4, so if you have s, it would be s to the 4, s to the 3, 2, 1, 0, right? And then you're going to have as many columns as you need. The number of columns that we'll need is actually, so the number of rows is n plus 1, right? The number of columns that we'll need is actually the ceiling function of n plus 1 over 2. Just kind of works out that way. But how we actually construct it, we don't have to memorize that. What we can do is we could just stick So A0, A1, A2, A3. So we go back to our polynomial. So A0, A1, etc. So we're just picking off the coefficients of the polynomial, right? And we're just plopping them in here in a zigzag pattern. So we stuck the first one in this first spot. Then we zigzag down here. So A0, A1, and then as we go down, then zigzag up diagonally, and then down 2, 3, 4, 5, 6, 7, right? 0, 1, 2, 3, 4, 5, 6. We put them in like that until we run out of coefficients. And after that, anything to the right when we run out of coefficients is 0. Okay? So that's the first two rows. We just take the polynomial and just plop them in there. Then we need to start computing these next rows from the rows above. And pretty much comes down to taking a 2 by 2 determinant to calculate each one of these things. Okay? So the first determinant we do, so the first coefficient we have to, first term that we need to calculate is B1, right? So B1 is, so I'll use a color for B1, choose a green color. So B1, I want to compute this. It is the determinant of this matrix. So it's a determinant of A0, A1, A2, A3 is that matrix, and then multiplied by -1 over this term. Okay? That's the first one. And there's a pattern that's going to emerge here, and so I want to show you guys. So I'm using colors here. And then I'll use orange. So then the next one is B2. So I want to compute this one. We're going to actually multiply the determinant by -1 over A1, the exact same factor that we multiplied by B1. And actually every one in this row, all the B's, will be all of these determinants that we're going to compute are going to be multiplied by -1 over A1. Okay? The determinant, though, is going to be of the matrix that's made up of this column and this column. Okay? So A0, A1, then we skipped a column, then A4, A5. So we still use this first column, but we use, instead of the second column for the other column of our determinant matrix, we are using the third. And then to establish the pattern thoroughly, the next one is going to be, once again, we're going to use this term, and we're going to use this column, the first column. But we're going to move one more over again for the second column, and that's going to be this column. Okay, so there's this visual pattern that emerges, and I recommend. So I also defined them here. I recommend just remembering the visual pattern. At least for me, it's way easier to remember the visual pattern than to remember which indices you have to use. I'm not very good at remembering that. So you always use the first column, and then you bump over a column for all of the determinants thereafter. It's not too bad. And then we move down to the next row. So eventually we're going to start getting zeros out here, right? Because these will have zeros. And then when we have a determinant of something, x, y, if you have a column of zeros, then that's always going to end up being 0, right? This times 0 minus this times 0, or minus y times 0. X times 0 minus y times 0, so it's always going to be 0. So eventually we get to zeros. And once we get to zeros, that we know are going to continue because we hit the 0 section, we can stop calculating. We know that everything else is going to be 0. And then we go to the next row. So the C row is the same exact algorithm, but shifted down. So let's use yellow haphazardly. So C1 is going to be found by the determinant of this column and this column, multiplied by -1 over this term. Okay? So we did the same thing. We shifted it down a row, and then, to give you one more, we'll use brown. Never used brown in my life in this program. Brown, and we're going to use this column again, and we're going to shift it over one, do this column. Okay? So, yeah. Yeah. So that is what this says to do. And then notice that when you get down, so here's down at the bottom, it starts to, this sort of naturally triangles, if you can use that as a verb, down to, so there's going to be zeros out here, and it's going to whittle itself down. When you get to S to the 0, you're going to just have one term. Actually, S to the 1 should be one term, and S to the 0 should be one term remaining. Okay? That are non-zero, or potentially non-zero. So sometimes these terms will be 0, and sometimes there is an exception, or so the exceptions that we aren't going to cover in class today, but are in the Nice textbook, is what happens if one of these terms in the first column shows up as a 0. That's the first exception you got to worry about. And the other one is if a whole row is 0, but you're not at the bottom yet. What do you do? And there's special ways of dealing with those two situations. Okay. All right. So that is the Routh table. The second step is the easier step, and that is to interpret the Routh table for stability purposes. For the basic Routh table, no poles lie on the imaginary axis. So those exceptions that I mentioned, those occur, one of those exceptions is what happens when you get an imaginary axis pole, okay? So for the basic Routh table, if you go along and you never have a 0 show up in your first column, and you never have a row that's all 0, then you have yourself a basic Routh table, right? Then you know, first off, that no imaginary axis poles exist, okay? That's the first thing. So the interpretation is simple from there, okay? And this is the Routh-Hurwitz criterion for a basic Routh table. The number of sign changes in column 1 is equal to the number of poles in the right half plane. And all the others are in the left half plane. So if you look down your first column, and your A0, your A1, your B1, C1, D1, all the way down G1, if they're all positive or they're all negative, you have 0 sign changes among them. And therefore, you have 0 closed loop poles in the right half plane. If you have 0 closed loop poles in the right half plane, you have 0 poles on the imaginary axis. What must be true about your system?
It almost be the left side.
It must be on the left side, and therefore, in terms of stability, it's stable. So that means you're stable. So if you build this, you know that if these are all positive, then your system is stable. Okay. If you build it and there are 2 sign changes, so say they're all positive up until B1, and then B1 is negative, and then the C1's positive, and they stay positive thereafter. How many sign changes is that? 2. You went from positive to negative to positive. Okay. So that means there are two closed loop poles in the right half plane, and therefore your system is unstable. If you had like a 10th order system and two of them end up in the right half plane, the system's still unstable, right?
How many do you need in the right half plane to be unstable?
Just one.
Just one?
All you need is one. Yep. Yep. It's like the, what do they say, the bad apple? It just spoils the whole bunch.
One fly room batch.
Unless you're talking about American food standards, in which case, like 3.4 flies is okay.
Yeah. In my thing, you get one fly and turns vinegar.
Okay, so therefore the system is strictly stable if the Routh array is of the basic type and has no sign changes in column 1. And we're going to do an example now. Notice that, well, we'll do the example. I think that's the best way to proceed. So, given the closed loop transfer function here, where k is a design parameter. So look at this. The denominator has a design parameter in it, k. So we can't solve for the roots of this. I mean, it's cubic, so technically there is a solution, but it's messy, okay? It's a messy solution. If this was 4th order or 5th order, it would get really crazy. Use the Routh-Hurwitz criterion to determine the range over which this system represented by this transfer function is stable in terms of the gain, or in terms of the parameter k. So let's proceed as you expect. So what's our first step? Let's build the Routh table. Should be capitalized. It's a name, Routh table. So I'm going to write it on the left-hand side in a sort of generic form, and then we're going to compute the unknown terms in it, and then we're going to write the filled in one on the right-hand side. So let's go ahead and first draw our column here. So we have s cubed is the highest order, s squared, s to the 1, s to the 0. Those are our columns. Those are our row labels. And then our columns, so n is 3, so if you wanted to use the little algorithm, or the little formula for it, it's going to be 4 divided by 2 is 2. Ceiling function of 2 is 2. So you only really need 2 columns. But I'm going to put in 3 columns just to show you the zeros in the third column. So we have to do well, I'm going to actually fill in the a's, because the a's we just read off. So the first one is 1, right? A0 is 1. And then we go, and then the next one down is 3, and we go down, and then we zigzag up to 1. And then what's the last one? K. Good. And we ran out, so we know everything after that is 0, right? And then that just keeps going. Zeros. So our next row then, let's say that we were a little unsure. There's going to be, so B1 is the first one. We're going to be a little unsure. Is this supposed to be 0? Actually, if you go back and look, the last two, whoops, used to going up. The last 2 rows have just one potentially non-zero term in them. So we really only need to have a B1 and a C1. But let's say we didn't know and we're going to put a B2 in here, just in case we like screwed that up. We should be able to compute 0, right? I mean, there's 0 because we compute them to be 0, so we don't have to compute it. We know it's supposed to be 0. And then we're going to compute, I'm going to compute B1, B2, C1 down here, and then we're going to fill in this Routh table here. So S cubed, S squared, S to the 1, S to the 0, and then 1, 2, 3. So we know it's still going to be 1, 1, 0, 3, K, 0, and then we're going to fill in these last ones. Okay. So computing the unknown values we get. So what is our B1 going to be?
-1.
So it's going to be negative, so we look here, so negative 1 over 3, right? Because from the if we look at the coloring here, so we're going to divide, so everything's going to be, all the b's are going to be multiplied by negative 1 over 3. Okay? And negative 1 over 3 times the determinant of which matrix?
1, 3, 1, 2.
Yeah, so take that first column, always that first column, and then you take the next column because we're in the first B calculation, and that is 1 times k is k minus 3 times 1 is 3, so we have negative 1/3 times k minus 3, which is equal to 1, switching the terms here, so 1 minus k over 3, which I think is slightly simpler way to express it. Okay, so there's B1, so that one's done, so we can just stick that right in here, right? 1 minus k over 3, that's the first one. B2 is equal to, once again, it's going to be negative, all the b's are going to be negative 1 over 3 times the determinant of something. So it's always the first column, 1, 3, and then what is our second column? 0, 0. And we have 1 times 0 is 0, minus 3 times 0 is 0. So we're going to have 0 here, and it's a little cramped there, but yeah, there's 0, and then these are all going to be 0 thereafter. So we didn't really need to compute it. We knew it was going to be 0, but it's good to see that once. That's 0. All right. Now we have just C1 to compute. C1 is going to be, what is, it's negative 1 over what? 1 over B1, which is 1 minus k over 3. So maybe I'll make that fraction a little bigger. And then the determinant of, so it's actually 3, so we take the one above it. So 3 B1, which is 1 minus k over 3. B2, which is 0. and oh wait, no, k, right? This one, k, and then b2 we say is 0. Right. Good. So we are ready to go. 3 times 0 is 0 minus, so I'll rewrite negative 1 over 1 minus k over 3. Negative sign's in a funky spot. Times, yeah, so it's negative, and I'm not gonna distribute it. I'm actually going to say it's negative k times 1 minus k over 3, right? The reason I didn't distribute it is that I did this problem last night, and the 1 minus k over 3 is canceled, right? Conveniently, and the negatives canceled too, so we end up with just k. Nice. So this last term in our Routh table is just k, and then the rest are 0. So we finished step 1, which is build the Routh table. Step 2 is to interpret the Routh table, right? So notice our k is in here, so we don't just get to go down the row and say, you know, everything is good or not good. So interpret. But we do know that since 1 and 3 are positive, if these second, or if the third and fourth terms are also positive, then we have stability, right? So now we have inequalities we can write. Ooh, remember inequalities? So fun. Okay. Interpret stable if 1 minus k over 3 is greater than 0, and k is greater than 0. That's this term. So 1 minus k over 3 is this term, and k is this term. So we're stable if those two things are true. So this one we can rearrange. This, we can add k over 3 to both sides and then multiply both sides by 3. We don't have to switch the direction of the inequality. Remember, you do if you multiply by a negative number, but positive number 3 you don't have to. And you get that k has to be less than 3, right? So this one says that k has to be greater than 0. This one says k has to be less than 3. So stable if, I'm going to say just all that implies 0 less than k less than 3.
What do you say about that switching the sign, switching direction stuff?
Oh, if you have an inequality, like if you said x is maybe like negative 3x is greater than y, if you wanted to solve for x, you have to multiply both sides by negative 1 over 3, right? And that's going to switch you have to switch the direction of the inequality then. So
Multiplying by negative.
yeah, since you're multiplying by a negative. So you just say x is less than negative 1 over 3y. I know, it's hard to remember some of those rules, but it makes sense if you think about it. Okay, so that is all on Routh-Hurwitz criterion I'm going to go over. It's not too bad, I think. It's an algorithm, and algorithms are easy. You just have to learn them, right? Okay. You're going to have some homework on that. So that's the end of this. Did anybody have any questions before I move on from the lecture? Routh-Hurwitz criterion?
So are all the homework problems, what homework is on us due today?
I don't know. Let's look. I'm going to stop the lecture there.